want to do 14.2 number 45, which is basically find some partials and interpret them.
Yeah.
And they give us the law of gravitation.
Mm-hmm.
So G is some capital G m over r squared.
Yeah.
Okay, so what was your earlier question, Vic?
Are those 4 different variables?
It is
Yeah, so are these 4 different variables?
not really. It's just showing that G is a function of M and R.
Okay, so this little g is a function of m and r, and this thing is,
One big old constant.
It's the
Yeah.
gravity.
yeah, that's the universal gravity constant. So that g is constant. This little g is really g as a function of m and r, right? Okay, so I've got one function label, one constant, and 2 independent variables. Gets cool with that? I want to calculate the partials with respect to, of course, the 2 independent variables, right? Okay, so what do you get when you calculate the partial of g with respect to m?
It's G over R squared.
G over r squared. Perfect. And I might think about this thing as a function of also m and r, right? You guys see that? This one, however, right, no longer depends upon m, right? It's independent of the mass. Okay, and then this guy, partial of g with respect to r.
Negative 3gm over r.
Negative
cubed.
2. Yeah,
Two?
negative 2 r cubed.
Wait,
Yep.
am I going the wrong way?
Still need the M.
Still need the m.
And I still need an m.
Oh, okay. I went too fast. Oh, I went too far.
Yeah, so that was saying, all right, this is gm r to the minus second power, right? Left the constants, the g and m, took the minus 2 down, got r to the 1 lower power. Cool? All right, so what do these mean? Right, this is the answer for part A. Check, done.
Yes.
What do these mean is kind of the question for part B. So,
Slope of the function when in terms of M is constant. Or, oh.
Well,
No,
the slope of the components
Yeah.
of the
It's
function
positive and constant.
that you could add together to get the gradient effect, right?
okay, so
Well,
you're
not add
thinking of
together,
these
but
as the
make it
components of a gradient vector? Sure. We didn't have gradient vectors when we were doing this one.
Right. Okay.
So what is this partial of g with respect to m? What is that? What's the interpretation of that thing?
How G changes
With
when
respect
M
to
changes.
With
Yeah,
respect to
so-
horizontal,
If I adjust the mass a little bit, right, how much stronger does gravity get? You guys all see that? So here's your rate at which gravity gets stronger for adding mass.
Yep.
Yeah, it shows no dependence.
That really says, right, that gravity is linear in mass, right?
Yeah.
You guys all see that? Okay, so then this other guy, what's this thing? Partial of g with respect to r, how do you interpret that?
The radius.
Yeah, that's the change in gravity as you wiggle the radius, right?
The radius of what?
Ah,
The planet.
so this is, I've got some planetary blob, right? And some other little object that's being attracted to the blob, right? This. Alright, so we wanted to interpret m and r, right? So we've got some planetary mass, some little object that's getting sucked into it. There's a distance they are apart, and a mass that this thing has. So this first term is, what if you increase the mass a little bit? How much harder does it pull, right? And this thing is, if you increase the radius a little bit, how much harder does it pull?
Harder.
Less.
Oh,
Yeah, it's less, right? This is negative, right? So the gravity's going down as I get further away. Does that make sense?
Yeah.
Yeah. And the rate at which gravity's going down depends on the radius you're already at. You guys see that? This thing doesn't care about what mass I was already at. Right, the increase in gravity is still the same. But this guy cares about what radius you were at and also what mass you were at. Cool?
Is there an equation that
Wouldn't you just rearrange?
Yeah, so if I wanted to know, if I knew a gravitational pull and I wanted to know a mass, I'd just kind of solve this thing. Right. Another thing we could think about is I know how to graph a function like this, roughly. Right.
Yeah.
I might look at this as being some constant
Multiplied by 1 over x.
times 1 over r squared, right? You guys see that? I know how to draw 1 over r squared.
ln.
It looks like this, right? You guys see that? So in one direction, right, it looks like this. And in the other direction, it's linear, right? You guys all see that? So I get this thing kind of swept out and up, right, along lines. You guys see that? That's a hard surface to draw, of course, but
Yeah.
maybe we can take a crack at it. Yeah, this is, of course, horrible, right? I'm not doing a good job drawing that.
It's supposed to be on the Z or the same.
Yeah, so those are supposed to be moving back in the M axis, right?
Yeah.
This is not a great drawing.
Oh, I see it now.
Cool. But roughly that's what's going on in the slopes, right, that I'm seeing.
You needed to arc that line.
This guy's the slope of that line. And this guy's the slope of one of these, right, depending on where you are.
That straight line, you needed to arc it, not have it straight. That's why I was having a hard time seeing it.
Still linear.
No, it needs to be linear.
Well, I meant to see the shape that it's going to become.
Yeah, it needs to be not parallel to this, right?
Yeah, straight line, not
Yeah, and I didn't do a great job with it. I should have made it less parallel, but